In the absolute vacuum of a dark void, something impossible is happening. We are witnessing the birth of order from pure chaos. Look closely. These are not digital renders. This is the fundamental architecture of our universe. Why does a jagged, chaotic world insist on building itself into perfect, razor-sharp geometric shapes? Today, we go beyond the surface to understand the violent, beautiful physics of crystal nucleation and why what you are seeing right now shouldn't actually exist according to the second law of thermodynamics.
Everything starts with a single mistake. In a supersaturated solution or a cooling melt, molecules are frantic. They collide billions of times per second. But suddenly, a cluster reaches a critical radius. If it's too small, it dissolves back into the void. If it hits that magic threshold, it becomes a seed. This is the moment of nucleation. But there is a hidden gatekeeper here, an energy barrier that prevents most structures from ever forming. What decides which atoms get to build a kingdom and which are forgotten?
Crystals are governed by the Bravais lattices, 14 unique ways that atoms can pack themselves into 3D space. As you watch this structure grow, it follows a strict mathematical script. It cannot deviate. It is a prisoner to its own chemistry. Whether it's a cubic salt grain or a hexagonal quartz pillar, the angles are locked. But here is the mystery. How does an atom on one side of a crystal know where its counterpart on the other side is supposed to land to maintain perfect symmetry?
There is a war happening at the boundary. The crystal wants to grow because it lowers its internal energy, but it costs energy to create a new surface. This tension is called surface Gibbs free energy. If the environment is too hot, the crystal melts. If it's too cold, it becomes a glass, a disorganized mess. The slow motion growth you see is a perfect thermal balance, a knife-edge walk between total liquid randomness and frozen solid perfection. If crystals were perfect, they would actually grow thousands of times slower than they do. So why do they move so fast? The secret is a screw dislocation. A tiny defect, a spiral staircase in the atomic layer, provides a permanent ledge for new atoms to grab onto. The crystal isn't growing in flat sheets, it's spinning itself into existence. Perfection, it turns out, is a bottleneck. Only the flawed can grow quickly. What does that say about the rest of our reality?
Why the dark void? Because gravity and convection are the enemies of purity. On Earth, rising heat creates currents that buffet the growing lattice, causing deformities. In the vacuum of space or a controlled dark void, growth is purely diffusion limited. This allows for whisker growth, crystals so thin and perfect they possess the theoretical maximum strength of their chemical bonds. They are hundreds of times stronger than the steel used in skyscrapers. Watch the facets form. This process is called Wolff construction. The crystal naturally chooses the shape that minimizes its total surface energy. It's a physical manifestation of an optimization algorithm. The flat faces we see are the planes where atoms are most tightly packed. They are the strongest walls of the fortress. As the void fills with these shapes, we start to see the emergence of what looks like alien architecture. But this isn't alien. It's the DNA of matter itself.
Where does that iridescence come from? It's not pigment. It's thin film interference. The layers of the crystal are so thin, measured in nanometers, that they divide light waves against themselves. Some colors are canceled out, others are amplified. As the crystal grows by even a single atomic layer, the color shifts. You are literally watching the thickness of an atom change the color of the universe in real time.
The growth is not peaceful. When two crystalline structures meet, they don't merge, they clash. This creates a grain boundary. These boundaries are the weak points where materials break, but they are also where the most interesting physics happens. In the dark void, as these structures expand, they compete for the remaining floating molecules. It is a slow-motion survival of the fittest, where the fastest-growing orientation consumes the others.
This isn't just a visual spectacle. This exact process is how we built the modern world. Every smartphone you've ever owned started as a single crystal silicon ingot grown in a vacuum. If we didn't understand the growth you're watching right now, the digital age wouldn't exist.
We are looking at the ancestor of the microprocessor, the foundation of every piece of tech that defines your life. As the last molecules in the void are consumed, the growth slows. The structure is now complete. For a brief moment, we have achieved a state of lower entropy in a localized area, a defiance of the universe's tendency toward disorder. But this perfection is fragile. A single vibration, a slight change in temperature, and the lattice could shatter. The void remains, but it is now occupied by a monument to geometry.
We started with nothing, and we ended with a masterpiece. Crystalline growth is the universe's way of telling us that even in the dark, there is a blueprint for beauty. If you found this deep dive into the microscopic world fascinating, hit the subscribe button and turn on notifications. We have much more to explore in the hidden corners of physics. What should we look at next under the macro lens? Let me know in the comments. Stay curious.